Okay, welcome back. Let us model an operating plant flotation rougher stage based on what we've modeled from the test work data. So these are the kinetics that we calculated from the test work data. Now we're going to construct a simple model for the rougher part of this flotation circuit in an operating plant. And that's an important distinction. And we'll deal with that shortly. We're in the flotation section. And in the flotation section, we need two types of reactors. We have a conditioner, and mathematically in the conditioner is where we set the kinetics for the flotation stage. And this is followed by a flotation cell. We also have some streams coming in. This is our feed. From the conditioner, it goes into the flotation cell. We have a concentrate takeoff, and we have a tails coming out the bottom. And as per the previous example, why don't we call this feed? We have conditioned feed. Let's call this a rougher conditioner, because we might add to this flow sheet a bit later with a cleaner conditioner. We have a flotation cell 1, but we can do better than this, rougher flotation. And this is rougher concentrate. And of course we have rougher tails. Right. Before we do anything, shall we make this a bit prettier? I think we will. I'm going to go select. Let's select all unit name labels. These ones get selected by default. You can do it one by one, but I chose to do it this way. And I want them red. No, it doesn't really work against that background. So I might just move them to where they were. Okay, now you know what's going to come next. Stream name labels. I want them bold as well, and I want them blue, and then the values here, we can leave them as is. Before we go any further, why don't we save this? I can't save it in this folder because there's already a .sim file. So I'm going to create a whole new folder, and let's just call it training 3, and full scale plant. I'm going to do this properly so we can audit what we've been doing. As I mentioned before, autosave is on, and we're also going to make use of this save backup feature once we've done something useful. So first thing we do is check that all our streams are connected properly. Yes, there should be one black stream, 2 reds and 1 blue. That's correct. And I can now save a backup just for fun. So graphic completed. It's a silly name. It's a good name. The first thing we need to do, this is empty. We need to define our feed. So we're going to open the stream setup. This flotation plant is going to operate at 100 tons an hour. And now obviously when it gets into the conditioner, we want about 15% solids. So I can calculate this will be 100 tons an hour. Okay, no, maybe 200. You know what? I don't know. I still don't know what the solids percentage is, but I have a little cheat. Well, this was 33%. I have another cheat, solids percentage target 15, enter, and it calculates my liquid flow for me. I could also have put another stream in here for water into the conditioner and solve so that it makes it 15%. This is a little shortcut because you need to do it so often. The minerals. Let's add some minerals from the database. Now we're going to do this slightly differently. I'm going to cancel that. We're going to close that, update and close. And I want to just make this a bit smaller so that we can see these minerals we had below. So, where were we? We were defining this stream. Now see, there's already data in. Now I don't need to right click and open the stream setup. I can just double click this stream. So we were going to fill in minerals. Let's add minerals from our database. So we know that there's magnetite in, and I made a mistake. However, if I type that in here, MGT, I get magnetite. The next one is quartz, QTZ. There's my quartz. The next one is calcite, talc, and pyrite. These are the minerals present. That's simple. What's next? Size classes. We can now fill in a whole size assay. We can create sieve sizes, for example, do a full ISO 565 test series, American standard, British standard, and we can do a square root series with a number of square root classes. However, we only have bulk data at this stage. So I don't even want to go through this, although when you press this button, it gives you a very nice size distribution. So I'm going to say, add me a 32 micron sieve. And all I have in this simple model is plus 32 micron, minus 32 micron, and they all behave the same. When you get different data, you treat it differently. And you can add it manually, or you can use one of these ones, which gives you standard sizes. Size distribution. Well, this is 20% plus 32 micron, and the rest is 80%. Doesn't really matter what you do now, we're going to treat them the same. And now we need to put in our mineral composition. Where's our test work data? Did we save it? Did we calculate it? Well, that's the thing. We did not. So we can now go back to Excel. We can go and look it up, what we had in the test work, or we can do this from scratch. So let's go to our test data. We shall put the feed, one up, thank you. There's our feed, 57%. Why don't we do what we did before? We'll get back to that one, keep this one on top. Shall we do some element to mineral stuff? I think we shall. What do we have analysis for? Fe, silica, silicon, lime, Mg, and sulfur. Okay, now if we select those and we type in the correct values, we'll be able to use this quite well. So let's have a look. Do we have the data on the right hand side? We do not. So we messed up. I'm going to close this one because there's an easier way to do all of this. So I'm going to discard and close this. I'm going to get back to this, save this model, Open up our test work data in HSC, which was this one, the rougher data. Now I don't want to save, I'll get back to it. I just saved it. We're going to go to our mass balancing section, and we're just going to go grab the data from this measurement data tab. Just copy all of this. That'll do us just fine. I'm going to paste it here. Why didn't it copy properly? We can fix that. Copy. Please paste. There we go. Welcome to the wonderful world of Excel, ladies and gentlemen. Freeze panes, so we can scroll up and get to. We didn't need to scroll up. We have the feed there. But more importantly, we have the feed mineral content. Yay! So we don't even need to do the element to mineral conversion, though we could. We're just going to type in these values, and that will do just fine. No, don't save any updates. Go back to our full-scale plant model. No, we don't want to save changes. Let's just go and see where we were. We were going to enter the composition. So we currently have only one mineral called ore. So perhaps we should go to minerals and add the correct minerals that we need. And clearly we didn't save them, which is a pity. So we have to now do it again. Isn't all of this interesting? So we're going to use the same order as this one just for fun. So the first one is magnetite. There is no hematite, but you know what? Let's just put it in. You'll see why shortly. Quartz, calcite, dolomite, talc, pyrite and goethite. These are all there, but we can just check. Yes, talc, pyrite and goethite are there. Press OK. Now I go to the size classes again. Add 32 micron, add sieve. And since there was nothing for minerals, did we have a flow rate? Yes, the flow rate was kept. Well, that's one good thing. Minerals are there. Size classes are now there. We said there was 20% plus 32 micron and 80% minus 32 micron. And that the composition was magnetite, 79.2%. And there is no shortcut. There was no hematite. The quartz was 18.43%. Calcite was 0.506. Dolomite was 0.931. Talc was 1.7. And pyrite was 0.0543. And there was 0 goethite. What do you mean minus 0.8 goethite? What mistake did we make here? Didn't all add up to 100, did it? So here's where these type of mistakes catch up to us. We are going to assume that there's a little less magnetite in this sample. Let's have a look at the head grade. It says that the head grade was 56.8% Fe. It should be 57.4. And the silicon was 9.12. We calculated 9.11. That's good. So we actually need more Fe. And Mg 0.45, Mg 0.32. We have too much Mg. But of course we said there was no dolomite, didn't we? And now suddenly we have a little bit of goethite, for which we have no kinetic data. So keep this in mind. We're going to continue with this example, but please note that, we can do things a bit better. I'm going to copy it for both size distributions. There's no need to go to total flow rate for liquids and gas. Just update and close. Our feed is defined. For each of these units, we need to select a unit model. So you right click, select a unit model. This brings up another screen where you can set for this one that has a tick mark. It's a conditioner. So let's find flotation conditioner. You know what? We can order by technology type. There's flotation altogether. Double click and the conditioner is now selected. And for the rougher flotation, it's either a flotation cell or a column flotation. Let's use a flotation cell. Apply and close. And now each one of these things have Excel or DLL models that do the calculations like you would normally do in Excel. I double click on the rougher conditioner and let's go and see what we have. And just before we go there, we're going to go and get the right test work data that we had. Did I overwrite my kinetic data? Well, this is embarrassing, but I can open it again. There we go. And clearly, yes, I did overwrite it. So first of all, we used a 3-component lab model. So we can choose the same model here, 3 components, so we can add the proper kinetics in. The flotation cell is 50 cubic meters and 4 meters high. Let's go and enter our model kinetics. Let's just get the order correct. It was magnetite, hematite, quartz, calcite, talc, pyrite, goethite. We're close. Why don't we just add in here a column for hematite? Then we have quartz, calcite, column for dolomite, talc, pyrite, and goethite, and GT right at the end. So this one was hematite, and we're going to say that these kinetics were the same. Then we had dolomite. We don't have kinetics for dolomite, so we're not going to put any kinetics in. And for goethite, the same. You know what? Why don't we do the same here? We don't have hematite. Let's not make up data. But now the order is correct. So for the fast kinetics, I can now copy this, Control C, paste, and I can also paste it to the second row by copying it, or I can just paste it again. So that's the fast mass proportions. The slow mass proportions, you know what's going to happen now. Copy, paste, paste. And then for the non-floating mass proportions, these are the mathematical differences that's taken care of. Now for the fast kinetics, the unit of measure is 1 per minute. So in this default one, 20% will float per minute. So for the fast flotation, so it'll take 5 minutes to float it all. But we have kinetics. So why don't we just copy those kinetics across because we did all this work. And then for the slow kinetics, we have data as well. So why don't we just paste all of that in? And that's it. This is now defined, and we can now save our model and save a backup. Let's just say kinetics defined. Okay, we have a backup so we can get back to this step in case we completely mess everything up in the next stage. Let's go and have a look at our flotation cell. We have one flotation cell in a row and we have one parallel row. Our flotation equation can be continuous or it can be batch. It doesn't matter what we choose here. It does not have to be the same as our lab batch samples. So I'm going to leave this on continuous because there's a point I want to make. The residence time calculation, feed volumetric, that looks good. And the lab residence time was 8 minutes. And it says for design reference. That's all. Scale-up factor is 1. And we have a net volume of 100 cubic meters for this one flotation cell. And we don't have any simulation data yet because we haven't run the model yet. But we're in a position to run it now. So let's go here. And this says we have 5 iterations. Let's just run the model and see what we get out. It was quite happy. And the input was our 57.4% Fe and all the minerals associated with it. We had a P80 of 32 micron and a P50 of 25 micron, etc. 566 water, as you remember, and we had a solids percentage of 15%. Our output out of the flotation cell, we had a concentrate and a tails, and it said that the concentrate was 68% Fe and the tails was 49% Fe. This is wrong. So something's wrong. Our streams don't go where they should. Let's go to this button called Stream Connections. And it says here that the tails is the concentrate stream and the concentrate is the tail stream. So I'm going to drag this tails one to just output streams again. And the concentrate goes to concentrate and the tails goes to tails. There's also a gas stream out and a gas inlet, so you can, say how many normal cubic meters of air you use per minute. You can put in launder water and you can have the feed. So that's how you define, if you have a water stream going in, that it goes into launder water. Right, how do you get out of the screen? You can't, except if you do this. So let's just, it has already swapped these streams for us, tails and concentrate. However, I like as good practice to just run it again. And there we go. So we have correctly defined a bulk operation, and it says that we get tails of 68% Fe and 49% in the concentrate. But those values are different than what we had in the test work data. Yes, they are. So shall we quickly deal with that? Minimize this one. Let's put this one there. Where's my silica? Okay, so our feed was 57.4. Input says 57.4. That's good enough. I'll just make this a bit smaller. Our tails was 71.5 and 0.9. Our tails here, output, is 68.4. And the silicon is 2.3. What's that in silica? Well, I don't know, but I also know that this test work data is in oxides. I need to do the same thing as we did at the start and just report silica as silicon. So shall we quickly do that? Um, let's do that here. Equals that divided by the molar weight of silica times the molar weight of silicon. Come on, computer. Thank you for checking for viruses. 0.4% silicon is what the data should be. And we had 2.3% silicon. Doesn't match. Modeling didn't work. This is all nonsense. Or perhaps we should just do something else. Shall we have a quick look at that? Perhaps the answer is very simple. Let's have a look at the rest of the output for this. It says that the residence time in this flotation cell was 8 minutes. The effective volume was 85%, 85 cubic meters. Could you remember that the original one was 100 cubic meters there? Sorry, we were on simulation data. It tells us the kilowatt hour or kilowatts. That gives us all sorts of data that we might need for design purposes. The second thing it does is it tells us that the tiles should spend 11 minutes in there, etc. We can do all these things. We can look at stage recoveries and then, enrichment ratios, concentrate divided by feed, then enrichment per mineral. I have a different idea. I just think that there's not enough cells. So I'm going to say, give me 2 cells in series, and I want 2 banks, 2 parallel banks. Okay? And I'm going to look at this output sheet and I'm going to press calculate. And this is going to change. Oh, well, that's interesting. Now I'm at 71.3% Fe and 0.54 silicon. And if I had to have 0.43 silicon and 71.52, so I'm getting close. So perhaps the simple answer was I needed more flotation cells. And that, of course, is the real answer. I just wanted to make this point. I still want 3 banks. No, I'll just want 3 cells in series instead of 2. I'm going to press calculate. And I'm going to have a look at my output data. And now we're at 71.4 and 0.49. Well, we're getting close, aren't we? And so I can now design this to give me whatever answer I think is practical, or that my other independent calculations say is a good grade recovery trade-off. There you go. However, since we want exactly the same answer, why don't we go to 9 in total? Give me 3 banks, 3 cells in series, and let's see what we get out of it. 71.41, 0.49, it didn't change. So, but I want to test that, and you can. So now you can go, I want 4 cells in a row. Solve. And what does that give me as an output? It didn't change. So we've reached equilibrium with 3 cells in a row, so we don't need 4 cells. Okay, so it's not my job to teach you how to design a flotation circuit in reality, but I did just want to make the point that the initial answer with 1 cell and 1 parallel row did not give us the right answer, and that didn't mean that the modeling was wrong, it just meant that we didn't allow enough time. Because in this case now, where we have 3 in series and we have 3 parallel banks, our residence time is significantly longer as it flows from one to another, etc. And that's the whole point. That concludes this series. You can read the rest of the documentation. You know what, let's do one more thing. Let's just get a reporting on this sheet a bit better. So first thing I want to do is I want to switch on visualization. And in my visualization, per default is 100 tons an hour, and that gives me my mass split. And that's not really useful for me. What I actually wanted to see was the, I don't know, calcium content. 0.2, 0.2, 0.25, 0.038. Okay, but I can only view one thing at a time this way, so I can also use the stream table editor. I'm going to open that. The stream title we're going to leave, and we click on this cell, and how many things do I want to report? Let's do 3 by 3. So we start and we just double click. So we have solids flow, we have liquid flow, and we want solid percentage. Then I want in each of the streams the Fe content, the silicon content, certainly lime or calcium content. I need another row and another column, actually 2 more columns. I do want a Mg content, and I do want an aluminium content, which isn't even here because we have no minerals containing aluminium. But we can add an amphibole to take care of that right at the start. And we can then do this all again, but we don't have to start from scratch. We can just add the minerals for aluminium stepwise through the process, calculate the kinetic data, go and put it into this model. So I'm going to make that 4 again. I also want the deportation. So the recovery percentage for Fe is going to go there. Thank you. For silicon, I want to see my silicon recovery. And you know what, let's just do it for all the minerals that we have here. And if I want to have minerals and sizing, etc., I'm going to put P80 in there because we might have data that does all that. And nothing changed because we need to specify what streams it should be reported on. And if we now apply and close, it actually displays for all the streams. As you can see here, the conditioner feed, it becomes superfluous because all this data is exactly the same as this data. The only difference is we've set kinetics per particle for flotation. So I'm going to go back in here and remove it from the conditioned feed. It does not add value in our reporting. Now legend is here on the top, and if I want to make it a different color, I can go into formatting and make this legend say on light blue, make sure there are all borders, main, apply and close, and the other tables are blue because I might want more tables. Please note that this is Fe silicon, calcium and magnesium. If I want the oxides, I cannot choose them. I have to build a custom table from here and just put in silica, CaO, MgO, etc. This concludes our series on building a flotation model. Hope you enjoyed it. Hope you can find some use from it. Thank you.